Alright, so here's another problem that we're going to use to solve. We're going to solve using conservation of energy. So, basically we've got a little guy here. Let's say this is you. You're trying to push a filing cabinet across a floor. And you are trying to push a 500 kilogram filing cabinet. And you can apply a force of 1,000 newtons. And what you're going to do is you're going to push this filing cabinet at a constant velocity the entire time for 5 meters. And what we want to know is we want to calculate our coefficient of friction for the system. Basically, this is a very simple problem, but you can kind of learn a lot about conservation of energy from it. So if we're going to draw our bar charts for this, hold on, let me fix this camera. Gets a little bit better. Alright, so if we're going to draw our bar charts for this, we're going to look at our system initially here. And what we'll have in our system is basically, if we're starting with constant velocity, we're going to have kinetic energy in our system. And we're going to assume that we're starting with a velocity here. So we'll have some kinetic energy in this system. And then on the other side, constant velocity, so we're going to have basically the same amount of kinetic energy in this system at the end. But we also have friction, so we're looking for our mu. That is our unknown in this case. So we definitely have some work due to friction here. We got kinetic energy final here and initial, so we got some work due to friction in our system. So here on this side we'll say 1/2 our mass times velocity squared, and 1/2 our mass times velocity squared. Alright, and then on our next part, well, we've got kinetic energy, work due to friction. Alright, what are we missing? Well, because these bar charts aren't equal, and they have to be equal because, well, that's conservation of energy. So we're missing our work done by our guy, alright? We're pushing on this filing cabinet, and if our filing cabinet is our system, well, work is being done on this system. So we definitely have some work being done on our system. And that work is going to be our force times our distance. And then we've got our work due to friction, which is mu, times our normal force, which is going to be g, times our mass, times our distance that we went. So basically what you learn from this problem is it's not too difficult to solve. Like, you could solve this right now. We're looking for mu, right? Right here, this value here. But we've got really a lot of unneeded stuff in the system. Like, first of all, well, we've got 1/2 our mass times velocity squared and 1/2 our mass times velocity squared. These are exactly the same because we have a mass and we have a constant velocity in our system. So this is because we have a constant velocity. If we didn't have a constant velocity, these would not cancel, but since we do have a constant velocity, these terms here just cancel, right? And if we're calculating our coefficient of friction, you can see that we actually don't need to know this distance here, our 5 meters. This was just a pointless, basically we could push it 10 meters, we could push it 20 meters. Our coefficient of friction is still going to be the same, so you can see that d here and d here cancel. So now we're just looking for our coefficient of friction, and now we just have these 3 terms here and our force being applied here. So sloppy now, but basically we're just looking for mu, right? So mu can be calculated pretty simply. Mu is equal to our force here, and then we're dividing out our gravitational constant and our mass of our system. So mu, if we look at this, we've got a force of 1,000 newtons being applied. We have gravity, and I'm doing numbers now. We have 10 meters per second squared, and then times our what was I doing? Our mass, which is going to be 500 kilograms here. So that is our calculation for mu. You can see that's very simple. Here is going to be 0.2. Can't do that in my head, that's bad. Anyway, basically that is an easy problem, but you can complicate it by seeing things that don't cancel, like our kinetic energy, and do a lot of useless calculations. And we also learned that it doesn't really matter how far we push this cabinet. We are going to always have a constant coefficient of friction between this cabinet and the same surface, as long as the surface isn't changing. So yeah, that's a basic easy way to calculate mu using conservation of energy.